problem that our project will solve is that going uphill is difficult for manual wheelchair users. Because they roll backwards between pushes, going uphill is difficult. This is a problem we now have firsthand experience with. To mitigate rolling backwards, users rush to get their hands back on the wheel after pushing forward. Because of this, they can't push as hard or as far with each stroke. The rapid arm movements that a user must do makes going uphill exhausting and puts additional strain on a wheelchair user's shoulders. A solution to this problem is to keep the wheelchair from rolling backwards down a hill. This problem isn't as simple as it first seems. First, wheelchair users need to move in reverse and turn on a dime on flat ground. Ideally, their movement on flat ground is not constrained by this device. Secondly, stopping on a hill can be dangerous. The picture on the right shows a user stopped on an incline. If the user were to lean back too far, the wheelchair could tip over backwards, a problem that we now have personal experience with. Because of this danger, if the wheelchair starts to tip backwards, the device needs to unlock the wheels. Finally, wheelchair users need to do wheelies over obstacles like curbs. In this instance, although the wheelchair is inclined and on the verge of tipping, the device must not impact their ability to roll forwards or backwards. Therefore, a device that keeps you from rolling backwards needs to sense the difference between flat ground, a hill, a dangerous event, and a wheelie, and respond accordingly. Existing devices to solve this problem have drawbacks. The manual grade aid shown on the right must be engaged by the user prior to each incline and uses teeth that can dig into and wear out the tire. If the user begins to tip backwards on a hill, this device will not be able to disengage to save them.
Shown on this slide is a sample of our design concepts that the team members came up with. After discussing the pros and cons of each concept among the team, we decided to move forward to the prototyping stage with 3 of the designs. This is because they all proved to be viable on paper and significant differences could not be evaluated without starting the build process.
Shown here is Preston working on one of our prototypes. Like Chase mentioned, we decided to move forward with 3 different prototypes. So you'll see pictured here our lever design, our jaws design, and our wrap spring clutch design. We ultimately decided to move forwards with our jaws design after testing all 3 prototypes. We'd like to show you a demonstration of our jaws design. You'll notice the red status light changes to green when Chase reaches the incline, indicating that the device is engaged automatically. He's able to remove his hands from the hand rims and rest comfortably while the device holds him firmly in place. Then he's able to keep moving forwards seamlessly.
Shown here is the final JAWS prototype installed on the device. The JAWS design utilized a spatially ratcheting system which acted near the hub of the wheel, keeping the device fully out of the wheelchair user's way.
Highlighted in this table are some of the key requirements our design was evaluated against. After iterative improvements, our design was able to meet all of the requirements listed here.
The prototype's current status has several smooth functioning components and a few parts that need some adjustments. The mechanical portions that work well include the device's ability to stop the wheelchair's backwards motion in less than 2 inches and the robust and reliable nature of the device. Areas that could use improvement include speeding up and widening the range of slopes the device can engage under load on and reducing the ratcheting noise it produces. On the electrical side, the electronic system worked. However, improvements could be made to how and where the batteries are mounted and other electronic components.